this lesson, we are going to focus on the radioactive elements and specifically what happens to an atom during radioactive decay. It is important to know, as we've been talking about these elements, that there is no chemical reaction that converts one element into another. So like these scientists at the bottom, if you wanted to take a big chunk of lead and turn it into gold, you can't do that. You can't turn one element into another element. However, elements do sometimes change into other elements on their own. For example, we'll look in a second that atoms of carbon can become atoms of nitrogen, and they do that because of radioactive decay. What that means is that some isotopes are unstable. And remember, we talked about isotopes. Those are atoms that have the same number of protons but different numbers of neutrons. Those are isotopes. And some of those isotopes are unstable, which means that their nuclei or their nucleus does not hold together very well. So through this process of radioactive decay, the atomic nuclei of the radioactive isotopes release these fast-moving particles of energy. So I'm sure you've heard talk about nuclear reactors, nuclear energy, nuclear bombs, all these different things. There are basically two types of nuclear reactions. So radioactive decay is an example of a nuclear reaction. And there are two types of nuclear reactions, both of which involve particles that are in the nucleus of the atom, which is why it's called nuclear. So these particles are in the nucleus of the atom, and something is happening that causes there to be a reaction. So in the first is nuclear fission. And in nuclear fission, that is a process in which an atom's nuclei splits apart. So the particles within the atom get split apart, and that's what we call nuclear fission. The opposite of that would be nuclear fusion. And what we know about the word fusion means that things come together. So in nuclear fusion is the process in which the atomic nuclei join together. So both of these are nuclear reactions. Fission is when the nuclei splits apart. Fusion is when the nuclei joins together or fuses. So how was all of this discovered? It came about actually kind of as an accident back in 1896. There was a French scientist, hopefully I get his name right, Henri Becquerel, who accidentally discovered the effects of radioactive decay. He noticed that when he had a mineral that contained uranium and it was exposed to sunlight, it gave off this energy that would sort of fog up and make these imprints on photographic film plates. And he thought that it was the sunlight that was causing this to happen. He thought the sunlight was necessary in order for this to happen. But what happened was he put these away in a drawer next to a photographic plate that was wrapped up in paper so that there was no sunlight, nothing going on. And then later when he came back, he found that there was an image of the mineral on the photographic plate. So it turns out that sunlight was not necessary at all. So that is when he hypothesized, whoops, I'm using the wrong thing. That's when he hypothesized that the uranium gives off energy called radiation all the time. So he concluded that. And then he presented that information to a young Polish researcher named Marie Curie, very famous name in science, as well as her husband, Pierre Curie. They are the ones then that sort of did more research, and they showed that a reaction was taking place with the uranium nuclei and that it was actually emitting radiation. So basically what happened is that Marie Curie is the one who discovered radioactivity. She did because of this. They didn't know the dangers of radioactivity at the time. She did eventually die from cancer as a result of her years of exposure to radium and uranium and all these different radioactive things. They didn't know at the time that they were quite dangerous. It's also important to note that Marie Curie, and that's whose picture you see on this page, she was the first scientist to win the Nobel Prize in 2 different subject areas. She won a Nobel Prize in physics. She also won a Nobel Prize in chemistry. Also, she was the first woman ever to receive a Nobel Prize. So she is one of our famous scientists that we look back at as making some major discoveries. She kind of came up with the X-ray machine that was used on the battlefields during war. But she was the first woman to receive a Nobel Prize and the first person ever to receive a Nobel Prize in 2 separate categories. On this next page, we are going to look at what happens as these atoms decay. This can get a little confusing with the terminology, so hold on with me here and kind of follow through. It's not complicated, but there's a lot of terms and lots of words that we have to think about. So first of all, let's go back to when we were talking before and remember that the atomic number is equal to, or is, the number of protons. So remember the atomic number on the periodic table, it tells you the number of protons, and that's what determines the element. So carbon is 6, carbon will always have 6 protons, its atomic number is 6. So the atomic number tells the number of protons, it identifies the element. So that's kind of our guiding thing that we need to know here. So the first type of decay I want to look at is alpha decay. During alpha decay, an alpha particle that consists of 2 protons and 2 neutrons, therefore it would be positively charged, has 2 protons, 2 neutrons, gets released by the atom during this decay. So the release of an alpha particle by an atom during alpha decay, what it does then is it decreases the atomic number by 2 and the mass number by 4. So let's look at this up here. So if this is the original atom, when it releases this particle, that particle is made up of 2 protons and 2 neutrons. So that this is what we end up with at the end. So we've lost 2 protons and we've lost 2 neutrons. So what that means then is that our atomic number, because remember the atomic number is the number of protons. So when we lose 2 protons, that means our atomic number goes down by 2. So it can no longer be the same element that it was before. Since it also lost 2 neutrons, and if you remember, the mass number is equal to the number of protons plus the number of neutrons. So what has happened here is that our atomic number has gone down by 2, which means it can no longer be the same element. The mass number, because it's protons and neutrons, has gone down by 4. So then what happens is, if this was thorium-232 to start with, it goes down by 2 protons, it becomes radium, becomes a new element, radium-228. So this is one type of decay, where it's called alpha decay. It gives off an alpha particle. That alpha particle is made up of 2 protons and 2 neutrons. So when it gives that away, the atomic number goes down by 2. The mass number goes down by 4. The next type of decay that we're going to look at is called beta decay. So during beta decay, a neutron in an unstable nucleus changes into a negatively charged beta particle and a proton. So instead of giving off the protons and the neutrons here, it changes into a negatively charged particle and a proton. So a beta particle is a fast-moving electron given off by a nucleus during radioactive decay. The proton that is created, that new proton, remains inside the nucleus. So the nucleus is then left with one less neutron and one more proton. So what happens then is that the mass number remains the same, but its atomic number increases by 1. So when it gives off this beta particle, the neutron changes into a negatively charged beta particle and a proton. The proton stays, the negatively charged particle leaves. So what happens then is that our number of protons increases by 1, but the mass number stays the same. So in this case then, since the proton number went up by 1, it went from being carbon to being nitrogen. It went up 1 place on our periodic table. The mass number stayed the same, so it was carbon 14 to nitrogen 14. The last that we are going to look at is gamma radiation. Gamma rays consist of high energy waves similar to X-rays. So if you can think of X-rays that doctors use to get pictures of your bones, those rays can go through your flesh, they can go through the muscle, but they can't penetrate through the bone, and that's how we get the picture of the bone. But both alpha and beta decay are almost always accompanied by gamma radiation. There's no charge, so it's not going to change anything. There's going to be no change in the atomic mass or the atomic number. So the atomic number stays the same, the atomic mass stays the same. It's just this energy that is being given off. All right, so we have alpha decay, where you give off this alpha particle. You lose 2 protons, you lose 2 neutrons. So your atomic number goes down by 2. Your mass number goes down by 4. Then we have beta decay, where the neutron in the unstable nucleus changes into a negatively charged beta particle and a proton. The proton stays, the electron goes away, so that causes our number of protons to go up by 1, but no change in the mass of the nucleus. And then we have gamma radiation, which is just that energy that is being given off. On this next page, I want to compare those types of radiation. We talked about X-rays and how it's able to penetrate through your flesh, through your muscle, through soft tissue, but not through the bone, and that's how we get to that image. So alpha particles are moving very fast. They can be blocked by just a sheet of paper, however. So we're talking here about the alpha particles, that first type of decay. They're going very quickly, and they could be blocked by a sheet of paper. So if this was the alpha particle, I guess I got green here. If this is the alpha particle, it will get blocked by the sheet of paper. They move very fast, but they get blocked by even just a sheet of paper. Alpha radiation can cause injury to your skin, so basically like getting a sunburn. When you're getting a sunburn, that's the type of damage that's caused by this. Beta particles are much faster and more penetrating than what the alpha particles are. They can pass through paper, but they might get blocked by aluminum that's about 5 millimeters thick. So here's our beta particle would go through the paper, but when it gets to the aluminum, it would get blocked and not pass through. Gamma radiation that we just talked about on the last page, however, is the most penetrating of the gamma rays. Back we talked about the electromagnetic spectrum. It's way, way down on the end of the electromagnetic spectrum. This is kind of interesting. You would need a piece of lead several centimeters thick or a concrete wall about 1 meter thick to stop gamma rays. So that means you would need a concrete wall about 3 feet thick in order to stop the gamma rays. So they deliver very intense energy to the cells and cause severe damage to the cell itself. Okay, I think we're going to stop there for today. Kind of go back and review the alpha, beta, and gamma decay back on page 109. Look through and answer all of the in-text questions that you have from page 106 through 110, and we will carry on the discussion tomorrow. Have a great day.